two solutions A and B, each of 100 liter, was made by dissolving 4 gram of NaOH and 9.8 gram of H2SO4 in water respectively. In that case, what is the pH of the resultant solution obtained from mixing 40 liter of solution A and 10 liter of solution B is? Now what we are doing here is hydrolysis of strong acid with a strong base, but the strong acid is a diprotic acid. We have 100 liters of A and we also have 100 liters of B. So A is NaOH and B is H2SO4. Based on the weight given, we first need to find out the molarity of A and B, and then from here we are taking 40 liter of NaOH mixing with the 10 liter of H2SO4. So therefore we have to find out the number of moles. We have to see which one is in excess, whether the H plus ions are in excess or the OH minus ions are in excess. If both are equal, then the pH will be 7. But if they are unequal, then we can find out the pH value, isn't it? So therefore, let's first determine the molarity of both of them. We know that molarity is equal to number of moles divided by volume in liters, and number of moles is equal to mass divided by molar mass. Molar mass of NaOH will be 1 time sodium, so 1 time 23, and then 1 time oxygen, 1 times 16, and then 1 times hydrogen, so 1 times 1, that is equal to 1. So therefore this will be equal to 40, and then molar mass of H2SO4 will be, we have 2 hydrogen atoms, so therefore 2 times 1, that is equal to 2. 1 sulfur atoms, therefore 1 times 32, that is equal to 32, and then 4 oxygen atoms, so therefore 4 times 16, that is equal to 64. So therefore this will be equal to 98. So this means number of moles of NaOH is equal to 4 gram divided by 40 gram per mole. So therefore this is equal to 0.1 mole, and then number of moles of H2SO4 is equal to 9.8 gram divided by 98 gram per mole. So therefore this is also 0.1 mole. Therefore molarity of NaOH is equal to 0.1 mole divided by 100 liters. So therefore that is equal to 10 to the power minus 3 mole per liter, and then molarity of H2SO4 is equal to 0.1 mole divided by 100 liter, and that is also equal to 10 to the power minus 3 molar. Now from here we are taking 40 liter of NaOH and 10 liter of H2SO4. When NaOH dissociates, it would dissociate as Na plus and OH minus. When H2SO4 dissociates, it would dissociate as 2 times H plus SO4 2 minus, isn't it? So this means number of moles of H2SO4 is equal to 2 times the number of moles of H plus ions. But to neutralize 1 mole of OH minus, we require 1 mole of H plus, isn't it? So therefore let's determine the number of moles of OH minus and the number of moles of H plus. So number of moles of OH minus is equal to molarity times volume. Molarity is 10 to the power minus 3 mole per liter. Volume is 40 liter. So therefore this is equal to 0.04 mole, and then number of moles of H plus is equal to 2 times molarity times volume. Why 2? Because H2SO4 is a diprotic acid. So therefore 2 times 10 to the power minus 3 mole per liter times 10 liter, and that is equal to 0.02 mole. So 0.02 mole of H plus will neutralize 0.02 moles of OH minus. So therefore 0.02 moles of OH minus is in excess, isn't it? We just have to subtract to find out the residual concentration. Therefore, the excess amount of OH minus that we have is 0.02 mole. So therefore, the concentration of OH minus is equal to 0.02 mole divided by total volume. Total volume is 40 plus 10. So 50 liters. Therefore, this is equal to 2 times 10 to the power minus 2 divided by 50. 2 by 5 is 0.4. So therefore, 0.4 times, when this 0 goes up, it would become 10 to the power minus 1. So therefore, 10 to the power minus 3, which we can write it as 4 times 10 to the power minus 4. Therefore, POH is equal to negative logarithm of OH minus ion concentration. Therefore, this is equal to negative logarithm of 4 times 10 to the power minus 4, and that is equal to log A times B is log A plus log B. So therefore, minus log 4 plus log 10 to the power minus 4. This minus 4 we can bring it to the front, and we have another minus outside. So therefore, that would become plus. Therefore, POH is equal to 4 minus log 4, because log 10 base 10 is 1. Log 4 we can write it as log 2 to the power 2, because log 2 value is what given in the question paper. Log 2 value is given as 0.3 in the question paper. Once again, we can bring this 2 to the front. So therefore, 2 times 0.3, and that is 0.6. So 4 minus 0.6, and that is equal to 3.4. That's the value of POH. Therefore, pH is equal to 14 minus 3.4, and that is equal to 10.6. So 10.6 is the correct answer here. 200 milliliter of 0.01 molar HCl is mixed with 400 milliliter of 0.01 molar H2SO4. What is the pH of the mixture is? We know that pH is equal to negative logarithm of H plus ion concentration. In this case, two ways one can make a mistake. One is when we are calculating the H2SO4 concentration, we have to multiply with the 2, because if we have 1 mole of H2SO4, how many moles of H plus ions we can get? We will get 2 moles of H plus ion, isn't it? We have H2 here. So therefore, we must multiply with 2, otherwise we can get a wrong answer. And another thing is, concentration and molarity are related, but they are not one and the same. Concentration is a general term for the amount of solute in a solution, while molarity is a specific term. When you say molarity, the volume has to be always in liters. Molarity is equal to number of moles divided by volume in liter. But when you say concentration, that is equal to total number of moles divided by volume. It is not in liter, it is just total volume. So total number of moles divided by total volume. So this part you need to be very clear about. Now let's calculate the concentration of H plus. So what would be the total number of moles here? That would be M1V1 plus M2V2. So in this case, we have to multiply the second one with the 2 because of this 2 factor here, divided by total volume is 200 plus 400, so 600. Therefore, this is equal to 0.01 times 200 plus M2 is once again 0.01 times volume is 400 times 2 divided by 600. So, this will be simply 2 because we have 10 to the power minus 2, 10 to the power 2. So, 200 is 2 times 10 to the power 2. So, therefore, this will be simply 4. So, 4 times 2 8 plus 2 10. So, 10 by 600, 1010 we can cancel. So, therefore, 1 by 60. So, this means pH is equal to minus log 1 by 60. We know that log A by B is equal to log A minus log B. Log 1 is 0. Therefore, this would simply become log 60. Log 60 we can write it as log 6 times 10, and we know that log A times B will be log A plus log B. So, therefore, this will be log 6 plus log 10 base 10 will be 1, and we know that log 2 itself is 0.3010. So, therefore, log 6 has to be greater than 0.3010. So, that means 1.14 is definitely wrong. Option 3 and 4 are also wrong. The only correct answer is 1.78. So, log 6 value is 0.78. Even though it is not given, we can guess that. So, therefore, option 2 is correct. Here is a question based on chemical dilution. An analyst wants to convert 1 liter of HCl of pH equal to 1 to a solution of HCl of pH equal to 2. The volume of water needed to do this dilution is how much in terms of milliliters? We know that as per chemical dilution, M1V1 is equal to M2V2, and the pH value initially is given as 1. So, therefore, the concentration of H plus ion is equal to 10 to the power minus 1, because pH is equal to negative logarithm of H plus ion concentration. So, unless we put 10 to the power minus 1 in the equation, we can't get pH equal to 1. Log 10 base 10 is 1. Therefore, initially the molarity is 10 to the power minus 1. Initially the volume is 1 liter, and then the molarity when the pH is equal to 2 is 10 to the power minus 2. And V2 we need to figure out in liter, and then we have to convert into milliliters. But the value of V2 is not what they are asking. So, we need to be a little bit careful here. What they are asking is the difference, the volume of water needed to do this dilution. That means from 1 liter to how many liters. So, we need to take the difference. Okay. So, therefore, 10 to the power minus 1 times 1 liter is equal to 10 to the power minus 2 times V2. Therefore, V2 is equal to 10 to the power minus 1 divided by 10 to the power minus 2, and that is equal to 10 to the power minus 1 times 10 to the power 2. So, therefore, it is equal to 10 liters. Therefore, in terms of milliliters, V2 equal to 10,000 milliliter. 1 liter equal to 1000 milliliter. So, therefore, the difference is 9000 milliliter. So, therefore, 9000 is the correct answer, because initially we already have 1 liter. So, from there how much water we need to add so that the pH will become 2. So, therefore, 9000 milliliter is the correct answer. What is the pH value of 0.001 molar sodium hydroxide solution is? We know that POH is equal to negative logarithm of OH minus concentration. Here the concentration of OH minus is given as 0.001 molar, which we can write it as 10 to the power minus 3 molar. Therefore, POH is equal to negative logarithm of 10 to the power minus 3. So, we can bring the minus 3 over here, that will become positive, therefore 3, and log 10 base 10 is 1. So, this means that pOH is equal to 3. Now, we need to find out the pH value. We also know another equation, that is pH plus pOH should be equal to 14. So, this means pH is equal to 14 minus 3, and therefore, that is equal to 11. So, the pH value of 0.001 molar NaOH solution is 11. At 298 K, the solubility of silver chloride in water is 1.434 times 10 to the power minus 3 gram per liter. The value of minus log Ksp for silver chloride is how much? Masses of silver as well as chlorine are given. At equilibrium, silver chloride solid in the aqueous medium would dissociate as Ag plus Cl minus. What this means is that if we have 1 mole of silver chloride, we would get 1 mole of Ag plus and 1 mole of Cl minus. Therefore, if the molar solubility of silver chloride is S, then the molar solubility of Ag plus is also S, and the molar solubility of Cl minus is also S. Therefore, solubility product, we can write it this way. Solubility product is equal to product of molar concentration of the constituent ions raised to the respective stoichiometric coefficients. Here the stoichiometric coefficient is 1 everywhere. So, therefore, this is S to the power times 1 times S to the power times 1. Therefore, this is simply equal to S square. Now, in the question, the solubility is given, but for molar solubility, the unit is mole per liter. So, how to convert gram per liter to mole per liter? We know that number of moles is equal to mass divided by molar mass. Here mass is given, but it is given in gram per liter. Therefore, if we divide by molar mass of silver chloride, then we can get mole per liter. The mass of silver is 107.9 gram per mole, and the mass of chlorine is 35.5 gram per mole. So, therefore, 9 plus 5, 14, remaining 1, 8 plus 5, 13, remaining 1, 1 plus 3, 4, 1. So, it is 143.4 molar solubility is equal to 1.434 times 10 to the power minus 3 gram per liter divided by 143.4 gram per mole. Gram would cancel. When the per mole goes up, it will be mole per liter. And this one we can write it as 143.4. So, therefore, this 10 to the power minus 3 will become 10 to the power minus 5. So, 10 to the power minus 5 molar, that is the molar solubility. Therefore, this is equal to 10 to the power minus 5 whole square. So, when the exponents x to the power a to the whole power b, we can write it this way, x to the power a times b. So, therefore, this will be simply 10 to the power minus 10 Ksp is. So, now they are asking minus log Ksp. So, therefore, let us take log on both sides. Minus log Ksp is equal to minus log 10 to the power minus 10 base 10. Using the logarithmic properties, we can bring the minus 10 over here, because if we have log x to the power b base a, we can write it as b times log x base a. So, using that property, we can write it as 10 times log 10 base 10. We know that log 10 base 10 is equal to 1. So, therefore, this will be simply 10 minus log Ksp will be simply 10. Therefore, 10 is the correct answer here. The solubility product for chromium hydroxide is given as 1.6 times 10 to the power minus 30. In that case, what is the molar solubility of this salt in water? Chromium hydroxide solid would dissociate as chromium 3 plus, because we have 3 here, plus OH minus. To balance the equation, we need to put 3 here, because here chromium lost 3 electrons. Therefore, 3 electrons must be gained here, because the number of electrons lost should be equal to the number of electrons gained. Therefore, if the molar solubility of chromium 3 plus is yes, then the molar solubility of OH minus is 3s. Solubility product of a compound is defined as the product of the molar concentration of the constituent ions, each raised to the power of its stoichiometric coefficient in a balanced equation. Therefore, here this is s to the power 1 times 3s whole cube, because we have 3 as our stoichiometric coefficient here. Here what we have is simply 1. Therefore, 3 cube is 27, s cube and s1. Therefore, that will become s to the power 4. Ksp value is given. Therefore, s to the power 4 is equal to 1.6 times 10 to the power minus 30 divided by 27. Therefore, s will be quartic root of 1.6 times 10 to the power minus 30 divided by 27. Therefore, option 1 is correct. If the solubility product of zirconium phosphate is denoted by Ksp and its molar solubility is denoted by S, then which of the following relation between S and Ksp is correct? First of all, we need to understand how we write salts and their dissociation. Let's say if we have a simple salt like NaCl, when it dissociates, it would dissociate as Na plus plus Cl minus. So, basically when we write salts, we write the cation first and then the anion. Therefore, if we have a sparingly soluble salt, let us say AXBY, then its dissociation equation can be written this way. It would give us X times A to the power Y plus, isn't it? We have to cross multiply, plus Y times B to the power X minus. So, to find out the charges, we have to cross multiply, and we know that Ksp is the product of molar concentration of the constituent ions, each raised to the respective stoichiometric coefficient. So, therefore, it would be A to the power Y plus to the whole power X times B to the power X minus to the whole power Y. Likewise, for zirconium phosphate, when it dissociates, it would dissociate as 3 times zirconium 4 plus 4 times PO4 3 minus. So, therefore, if we have 1 mole of zirconium phosphate, we would get 3 moles of zirconium 4 plus and 4 moles of phosphate ion. So, therefore, if the molar solubility of zirconium phosphate is S, then the molar solubility of zirconium 4 plus is 3S and the molar solubility of phosphate ion is 4S. So, therefore, Ksp in this case is equal to 3S to the whole power 3, because we have the stoichiometric coefficient 3, times 4S to the power 4, because we have the stoichiometric coefficient 4. So, therefore, this would be equal to 3 to the power 3, that would be 27 times S cube times 4 to the power 4, that would be 256. times s to the power 4. So therefore 256 times 27, that would be 7 times 6 42. So 2 remaining 4, 7 times 5 35 plus 4 39, remaining 3, 7 times 2 14 plus 3 17, 2 times 6 12, remaining 1, 2 times 5 10 plus 1 11, remaining 1, 2 times 2 4 plus 1 5. So therefore 2, 9 plus 2 11, remaining 1. So therefore 8 plus 1 9, and then 5 plus 1 6. So therefore KSP is equal to 6912 times s to the power 7. So therefore s is equal to KSP divided by 6912 to the whole power 1 by 7. This means option 4 is correct. Here is a tricky question from ionic equilibrium. 20 ml of 0.1 molar H2SO4 solution is added to 30 ml of 0.2 molar ammonium hydroxide solution. What is the pH of the resultant mixture is? The reason I said this question is tricky is because some students are thinking that they have to use the concept of limiting reagent here. No, you should not use the concept of limiting reagent here. Why? Because what we are doing here is making a basic buffer, and that too by adding a limited amount of strong acid to an excess of weak base. That's what we are doing here. So basically it is a partial neutralization reaction. Also, the concept of limiting reagent should not be used in partial neutralization with a basic buffer, because the reaction is typically reversible and reaches an equilibrium rather than going to completion. And we know that buffer systems are designed to resist drastic changes by maintaining a coexisting weak acid base pairs, leaving all components present rather than consuming one completely. In 100% irreversible reactions, you can use the concept of limiting reagent, but here you shouldn't, because if you invoke the concept of limiting reagent here, you would be really confused about this problem. So don't use the concept of limiting reagent for these kind of problems. So now we know that molarity is equal to number of moles divided by volume in liter. We have a diprotic acid, so let's find out the number of moles. Because we have a diprotic acid, the number of moles in this case is equal to 2 times molarity, that is 0.1 mole per liter, times volume is 20 milliliter. So this will be equal to 4 millimoles. So this is for H2SO4, and then for ammonium hydroxide, the number of moles will be equal to 1 time 0.2 mole per liter times 30 milliliter. So here it would be 6 millimoles. Let's write the acid base equation. We have ammonium hydroxide, so that is our weak base, and H plus, that is the strong acid, and we are getting salt of weak base, that is NH4 plus water. Initially what we have is, we have 6 millimoles of ammonium hydroxide and 4 millimoles of H plus. The change that is happening here is minus 4 millimoles, and here also minus 4 millimoles. Therefore here it would be plus 4 millimoles. So therefore at equilibrium we would have 2 millimoles of ammonium hydroxide remaining, and H plus will be 0, and here it would be 4 millimoles. And we know that POH is equal to pKb plus log concentration of salt divided by concentration of base. Value of pKb given here is 4.7 plus log concentration of the salt is 4 millimoles and concentration of base is 2 millimoles. So therefore this will become log 2. Log 2 is 0.3010. So therefore the value of pOH is equal to 5, and we know that pH plus pOH is equal to 14. So therefore pH is equal to 14 minus 5. Therefore pH is equal to 9. That is the correct answer. Therefore option 3 is correct. This is a simple question, but if you invoke the concept of limiting reagent and all, this question can make you very confused. So therefore do not invoke the concept of limiting reagent here. That is strictly no. This is a buffer solution. So therefore you shouldn't invoke the concept of limiting reagent here. 20 milliliter of 0.1 molar ammonium hydroxide is mixed with 40 milliliter of 0.05 molar HCl. In that case, what is the pH of the mixture is? We have to find out the nearest value. Now, this is an example of hydrolysis of salt of strong acid and weak base, basically cationic hydrolysis. Therefore, in that case, pH is equal to 7 minus half pKb minus half log C. C is the concentration of the mixture. Now, here we have ammonium hydroxide, which is the weak base, that we are mixing with the strong acid, that is hydrochloric acid, and we are getting the salt of weak base, that is ammonium chloride plus water. The stoichiometric mole ratio is 1 everywhere. In terms of number of moles, they are equal. But will the concentration be equal? No, they won't be, because the volumes are going to be different, isn't it? So in terms of stoichiometric mole ratio, everything is 1. And we know that concentration is equal to number of moles divided by volume. Or you can also say that molarity is equal to number of moles divided by volume. So let us first find the number of moles of ammonium hydroxide and HCl. The number of moles of ammonium hydroxide is equal to molarity of ammonium hydroxide is given as 0.1 molar times volume is 20 milliliter. So therefore this is equal to 2 millimoles. So this is for ammonium hydroxide, and then for HCl the molarity is given as 0.05 molar times volume is given as 40 milliliter. So therefore this would be 5 times 10 to the power minus 2. So 1010 we can cancel, and then 5 times 4 is 20. So 10 we can again cancel. Therefore this is also 2 millimoles. Now the concentration of the salt is equal to millimole of the salt, that is 2 millimole, divided by volume, total volume 20 plus 40, so 60 milliliter. So therefore this is equal to 1 by 30 molar. Therefore pH is equal to 7 minus 1 by 2. Kb value is given as 1 times 10 to the power minus 5. So that is basically 10 to the power minus 5, and we know that pKb is equal to negative logarithm of Kb. So therefore that is equal to minus log 10 to the power minus 5. So therefore this is simply 5. Once we bring the minus 5 to the front, it would become positive because we have another minus sign here, and log 10 base 10 is 1. So therefore half times 5 minus 1 by 2 log 1 by 30. So this is 2.5 here. So 7 minus 2.5. So 4.5 minus half, and then log 1 minus log 30, because log A by B is equal to log A minus log B. Log 1 is 0 and minus into minus will become plus. So, therefore, pH is equal to 4.5 plus half log 30. 30 we can write it as 3 times 10 and log A times B is log A plus log B. So, therefore, 4.5 plus 1 by 2 times log 3 plus log 10. Log 10 base 10 is 1. Log 3 value is given as 0.48. So, therefore, 4.5 plus 1 by 2 times 1.48. So, this will become 0.74. So, therefore, 4.5 plus 0.74, that would be 5.24. So, therefore, the nearest value is 5.2. Therefore, option 3 is correct. If 1 millimolar solution of ethylamine produces pH equal to 9, then the ionization constant Kb of ethylamine is 10 to the power minus x. What is the value of x is? We have to find out the nearest integer, and the condition given is degree of ionization of ethylamine can be neglected with respect to unity. So, this means if it is 1 minus alpha, we can take that approximately equal to 1. pH value is given as 9. We know that pH plus pOH is equal to 14. So, therefore, pOH is equal to 14 minus 9 and that is equal to 5. This means the concentration of OH minus is equal to 10 to the power minus 5 because pOH is equal to negative logarithm of OH minus ion concentration. So, unless we put the value 10 to the power minus 5 here, we can't get 5 here, isn't it? Log 10 base 10 is 1. Now, we have ethylamine which is a weak base, and in the aqueous medium it accepts a proton and gives us OH minus and ethyl ammonium ion. So, initial concentration that we have here is 1 times 10 to the power minus 3 molar because it is given in millimolar, and we will have nothing on the product side. But at equilibrium, the concentration of ethylamine will be C minus C alpha, which we can write it as C times 1 minus alpha, and we know that 1 minus alpha is approximately equal to 1. So, even at equilibrium, we are going to take the value as simply concentration. So, therefore, this is simply equal to concentration. On the product side, it would be C alpha, and we know that concentration of OH minus is 10 to the power minus 5. So, therefore, the concentration of ethyl ammonium ion should also be taken as 10 to the power minus 5. Therefore, Kb is equal to concentration of ethyl ammonium ion times concentration of OH minus divided by concentration of ethylamine. Water is in excess and therefore, we do not enter that in the equation. So, therefore, this is equal to 10 to the power minus 5 times 10 to the power minus 5 divided by 10 to the power minus 3. Why we are taking it as 10 to the power minus 3? Because C times 1 minus alpha is simply equal to C, because 1 minus alpha is approximately equal to 1. That is why we are putting the initial value that is given. So, therefore, this would become 10 to the power minus 7, and on the left hand side we have 10 to the power minus x. So, therefore, x is equal to 7. That is the correct answer. Which of the following happens when ammonium hydroxide is added gradually to the solution containing 1 molar A2 plus and 1 molar B3 plus ions? Solubility product of both the salts are given at 298 K. Now, we know that the condition to form precipitate is ionic product has to be greater than the solubility product. How AOH twice would break apart in the aqueous medium? It would break apart as A2 plus and 2 times OH minus. And how BOH thrice would break apart in the aqueous medium? It would break apart as B3 plus and 3 times OH minus. Now let us assume that we have a beaker that contains the solution of both A2 plus and B3 plus ions, and we are gradually adding ammonium hydroxide to this mixture. So this means depending upon the concentration of OH minus, we will get the precipitate. So we have to find out the concentration of OH minus first. Then we can take a decision for this question. So we know that ionic product, let's say for this one, we can write it as equal to concentration of A2 plus times concentration of OH minus square. So if this has to be greater than the solubility product, then A2 plus concentration here is given as 1 molar. So therefore OH minus concentration square greater than 9 times 10 to the power minus 10. So therefore the concentration of OH minus in this case, if we take a square root, then it would be 3 times 10 to the power minus 5 molar, isn't it? Now for BOH thrice ionic product, we can write it as concentration of B3 plus times concentration of OH minus cube, and the solubility product value is given as 27 times 10 to the power minus 18. So this is 1 molar. So this means OH minus whole cube is greater than 27 times 10 to the power minus 18. So if we take a cubic root, then this would become 3 times 10 to the power minus 6, isn't it? Because 27 we can write it as 3 cube. So then if we are taking a cubic root, what we are basically doing is 1 by 3. So that would become 3. Likewise for 10 to the power minus 18, if we put to the whole cube 1 by 3, it would become 10 to the power minus 6. Here the OH minus concentration is 3 times 10 to the power minus 6 molar. But which one is smaller? This concentration is smaller compared to what we got here. What this means? This means that we require a very small amount of OH minus from the ammonium hydroxide, and that would make a precipitate of BOH thrice. Because if you do a back calculation for both of them, what will happen is ionic product would be equal to solubility product in both the cases. That means the solution is exactly saturated. But to make a precipitate, that means to make a solution super saturated, we have to exceed the solubility product. IP value has to exceed the solubility product. So this means the OH minus concentration has to increase. But when we are adding ammonium hydroxide, we need a very small amount of OH minus to make a precipitate of BOH thrice. To make a precipitate of AOH twice, we need much more concentration of OH minus. That's the difference you need to understand in this question. Because here it is 3 times 10 to the power minus 5 and there it is 3 times 10 to the power minus 6. So therefore we need a smaller amount of OH minus concentration to make a precipitate of BOH thrice. This means BOH thrice will precipitate before AOH twice. So therefore option 1 is the correct choice here. If equal volumes of AB2 and XY aqueous solutions are mixed, which of the following combinations will give a precipitate of AY2 at 300 K? Solubility product of AY2 at the same temperature is given as 5.2 times 10 to the power minus 7. We know that when the reaction quotient is greater than solubility product, then precipitate will form. Reaction quotient means in this case ionic product. If the ionic product is greater than the solubility product, then precipitate will occur. So here we have AB2, that would dissociate as A2 plus B minus. We have to put stoichiometric coefficient 2 to balance the equation, and we have XY, that would dissociate as X plus Y minus. By mixing these two, we are getting AY2. Therefore, AY2 at equilibrium would dissociate as A2 plus 2 times Y minus in the aqueous medium. So, if the molar concentration of AY2 is S, then the molar concentration of A2 plus is S, and the molar concentration of Y minus is 2S, because we have the stoichiometric coefficient 2 here. So, therefore, KSP is equal to S times 2S to the whole square, and that is equal to 4S cube. So, 4S cube value is given as 5.2 times 10 to the power minus 7. When we write ionic product, we write it in terms of concentration, isn't it? Concentration of A2 plus times concentration of Y minus whole square. Now, the expression for the solubility product and the ionic product appears to be the same, but in the solubility product expression, the molar concentration represents the equilibrium concentration, and in ionic product, the initial concentration or concentration at time t is used. This is very important to understand, because when we are saying concentration of A2 plus before mixing, that is what is given here. This is concentration of A2 plus before mixing. This is concentration of Y before mixing, because if you have XY, what it means by 2 times 10 to the power minus 2 molar XY? That means X plus concentration is 2 molar, Y minus concentration is 2 molar, but that is before mixing. But once you mix equal volumes, then what will happen? The volume will be doubled, isn't it? Then the total volume would change. Total volume will become 2 liter. That's the key part to understand in this question, because concentration is number of moles divided by volume. So, let us say if we are measuring the concentration of A2 plus, that is, let us say before mixing, then how we can write that? We can say this is number of moles divided by volume. So, let us say number of moles is 2 times 10 to the power minus 2 divided by volume is 1 liter, let us say. So, that is how we get into 2 times 10 to the power minus 2 molar, isn't it? Mole per liter is, we write it as capital M. Now, how about after mixing? Can we write the same thing after mixing? After mixing AB2 and XY, can we consider the volume as 1 liter? No, because here it is 1 liter, here also 1 liter. Therefore, the total volume has changed now. Therefore, everywhere we have to divide by 2. That's the key part in this question. So, let us check one by one. So, therefore, in the first case, we have 2 times 10 to the power minus 2. We have to divide by 2 now, because total volume is 2 liters, times 2 times 10 to the power minus 2 divided by 2 whole square, because we are checking the ionic product. So, therefore, this will be how much? This will be 10 to the power minus 6, which is greater than 5.2 times 10 to the power minus 7. That is the KSP value given. So, therefore, precipitate will occur. Let us check the other things also. In the case of 2, it is given as 3.6 times 10 to the power minus 3 divided by 2 times 5 times 10 to the power minus 4 divided by 2 whole square. So, this will become 2.5, this is 1.8. So, therefore, this will be somewhere around 10 to the power minus 11. Whatever the number that comes, it does not matter, because we already have 10 to the power minus 11, that is less than 10 to the power minus 7. So, therefore, 2 is definitely wrong. How about 3? 3, we have 1.5 times 10 to the power minus 4 divided by 2 times 1.5 times 10 to the power minus 3 divided by 2 whole square. So this will become 0.75. This is also 0.75. So already we are getting 10 to the power minus 10. So therefore that is less than 5.2, whatever be the value here, 10 to the power minus 7. So therefore 3 is also wrong. How about 4? 4 we have 2 times 10 to the power minus 4 divided by 2 times 0.8 times 10 to the power minus 3 divided by 2 whole square. So this becomes 0.4. 2 we can cancel. So this will be 0.16 times 10 to the power minus 10. Even if we write it as 1.6, then it would become 10 to the power minus 11, which is less than KSP. So therefore 4 is also wrong. So this means that option 1 is correct. Here is a tricky question from ionic equilibrium. The pH at which magnesium hydroxide begins to precipitate from a solution containing 0.10 molar Mg2 plus ions is how much? The reason I said this question is tricky is because it almost appears like ionic product is greater than the solubility product, but it is actually not, because they have mentioned begins to precipitate. So what it indirectly means is that there exists an equilibrium. The solution is saturated. It is not yet supersaturated. So this means ionic product is equal to solubility product. That's the assumption we should make here. So we know that magnesium hydroxide solid would dissociate as Mg2 plus 2 times OH minus in the aqueous medium. So if the molar concentration of magnesium hydroxide is S, then the molar concentration of Mg2 plus is S, and the molar concentration of OH minus is 2S. So therefore KSP is equal to S times 2S to the whole square, because we have the stoichiometric coefficient 2 here. So therefore this is 4 times S cube, and that's value is given as 1 times 10 to the power minus 11. And it is also given that the concentration of Mg2 plus is 0.10 molar. So therefore ionic product, we write it this way: ionic product is equal to concentration of Mg2 plus ions times concentration of OH minus square. So now, because of the assumption that solubility product is equal to ionic product, what we can do is we can compare that 1 times 10 to the power minus 11 is equal to 0.1 molar times OH minus square. So therefore 1 times 10 to the power minus 11 divided by 1 by 10, and that is equal to OH minus concentration square. When this 10 comes up, it would become 1 times 10 to the power minus 10, that is equal to OH minus concentration whole square. So if we take square root on both sides, then it would be 1 times 10 to the power minus 5. So therefore the concentration of OH minus is 10 to the power minus 5. So if we take log on both sides, so then it would be, and multiply with minus, then it would be log 10 to the power minus 5 base 10, and that is equal to minus log OH minus. So therefore we can bring this minus over here. So therefore 5 is equal to POH. We know that pH plus POH is equal to 14. So therefore pH is equal to 14 minus 5. Therefore pH is equal to 9. So that's the correct answer. So it would be 9. Keep it in mind that only when the ionic product is greater than the solubility product, then only PPT will form. If it is equal, what it means is that the solution is saturated. When it would become supersaturated? If the ionic product is greater than the solubility product, then the solution is supersaturated and we would see precipitate. Otherwise, we won't see precipitate. So here the OH minus concentration is 10 to the power minus 5. So basically we would have the same value if you multiply it. So basically we would be having exactly 10 to the power minus 11 if we multiply it, and that is equal to the solubility product. So therefore what we need to understand here is the solution is just saturated. Precipitate will form once the ionic product exceeds the solubility product. Here is a question based on Ostwald's dilution law. The pH of a 0.01 molar weak acid HX with a dissociation constant 4 times 10 to the power minus 10 is found to be 5. Now the acid solution is diluted with the excess amount of water so that the pH of the solution changes to 6. The new concentration of the diluted weak acid is given as x times 10 to the power minus 4 molar. What is the value of x is? We need to find out the nearest integer. Before I solve the actual problem, I would like to mention that for this question, this value would be slightly confusing to many of us. Actually, it would have been nice if it was given like 0.25 molar so that everything would be perfect. But mistakes happen in question paper sometimes. But what we need to understand from this question is that when the dilution increases, the degree of dissociation of the weak electrolyte also increases. That's what we need to worry about. So therefore, let us worry about the new pH, that is 6. So we know that pH is equal to negative logarithm of H plus ion concentration. If the pH is 6, this means that this is negative logarithm of 10 to the power minus 6, so that we can get 6 on both sides, isn't it? So therefore the H plus ion concentration is equal to 10 to the power minus 6. Now for weak acids, as per Ostwald's dilution law, we know that H plus ion concentration is equal to square root of Ka times C. So therefore 10 to the power minus 6 is equal to square root of 4 times 10 to the power minus 10 times C. So if we square it on both sides, then it would become 10 to the power minus 12 equal to 4 times 10 to the power minus 10 times C. So this will become 10 to the power minus 2. So therefore 4C equal to 10 to the power minus 2. Therefore C equal to 1 by 4 times 10 to the power minus 2. 1 by 4 is 0.25, which we can write it as 25 times 10 to the power minus 4. So that means the value of x is 25. So as I mentioned, it would have been nice if the question has mentioned the value of weak acid initially as 0.25 molar, but it is given as 0.01 molar. That may cause slight confusion. But what we need to understand is that when we dilute a weak acid, the degree of dissociation of the weak electrolyte increases. That's all we need to worry about it. So therefore 25 is the correct answer here. Only 1 liter buffer solution was prepared by adding 0.1 mole each of ammonia and ammonium chloride in deionized water. The change in pH on addition of 0.05 mole of HCl to the above solution is how much in terms of 10 to the power minus 2. We have to find out the nearest integer. Now we have a weak base and its salt. Ammonia is the weak base and ammonium chloride is its salt. So therefore we have a basic buffer here. Therefore as per the Henderson-Hasselbalch equation, POH is equal to pKb plus log concentration of the salt divided by concentration of the base. The salt is basically the conjugate acid. So therefore this is equal to 4.745. Initially what we have is 0.1 molar, isn't it? Because 0.10 mole divided by 1 liter. So therefore initially what we have is 0.1 molar of salt as well as base. So therefore 0.1 divided by 0.1, that is log 1. So that would be 0. So therefore pOH value is equal to 4.745, and we know that pH plus pOH is equal to 14. So therefore pH is equal to 14 minus 4.745. So therefore pH initially is equal to 9.255. So that's the value we have initially before adding HCl. Now we are adding 0.05 molar of HCl because it is mentioned 1 liter, and we know that HCl is a strong acid. So therefore ammonia reacts with the HCl, and then we would get ammonium ion plus Cl minus. Initially what we have is 0.1 molar, and then for ammonium ion is also 0.1 molar, and then we are adding 0.05 molar HCl. Because HCl is a strong acid, it would try to neutralize, isn't it? So therefore the change that would be happening is 0.1 minus 0.05, and here it would be 0.1 plus 0.05. So therefore at equilibrium the ammonia that we would be having is 0.05, and then the base concentration would be 0.15. So therefore the new pOH is equal to same pKb value, that is 4.745 plus log concentration of the salt, that is 0.15, divided by concentration of the base, that is ammonia. So 0.05. 0.05 times 3 is 0.15. So therefore this is log 3. Therefore pOH is equal to 4.745 plus log 3 value is given as 0.477. So therefore this is equal to 7 plus 5 12 remaining 1, 7 plus 4 11 plus 1, so 12 remaining 1, 4 plus 7 11 plus 1, so 12 remaining 1. So therefore this would be 5.222. So that is the value of pOH. So therefore 14 minus 5.222 should be the value of pH. So therefore this is 10 minus 2 8, 9 minus 2 7, and then 9 minus 2 7, and then 13 minus 5 8. So therefore pH value is equal to 8.778. So this is after adding HCl. Initial pH value that we determined was 9.255. After adding HCl, the pH value that we got is 8.778. So therefore 15 minus 8 7, 14 minus 7 7, 11 minus 7 4. So therefore 0.477 is what the change in pH is, but they want the answer in terms of 10 to the power minus 2. So therefore 47.7 times 10 to the power minus 2, nearest integer is 48 times 10 to the power minus 2. So therefore 48 is the correct answer.